Perfect. Okay, so let's go. Yes, Georg already outlined this a bit. I used to be a physicist, and over the course of my postdoc, at least, I have sort of degraded more and more into the depth of computer science and specifically AI research. So I joined the dark side. My junior research group is called Robust and Efficient AI. And the work I will be presenting here is partially stuff that I've been doing before and a lot of stuff that I've been doing together with Markus Götz. And to give you a glimpse of who is involved in all of these things that you'll be seeing. Is this working? Yes, this is us. This is the AI team at the Steinbuch Center for Computing. So the computing center at KIT. We are basically by now two groups. One is my junior research group that is funded by BMBF, and the other half, which is led by Markus Götz, is the so-called Helmholtz AI consultants team. If you've never heard about Helmholtz AI consulting, look it up. It's a cool thing. And together we do AI research for science and engineering. So I'm not going to be talking about ChatGPT. I'm not going to be talking about image classification. Still, I have a background in natural sciences, and this is still sort of what interests us most. And here at KIT, we do a lot of engineering research. There's a lot of physics, climate sciences, energy research. And this is sort of the turf that we are playing with. And when we look at these topics, there's two fundamental things that we ask ourselves when we go to scientific applications. One would be, what is this? And the other question is, what does it do? We don't care so much for the what is this part. This is more the physicists in particle physics and stuff. But what we here do, and what I've been doing for the past 10 years of my research, is what does it do? Because whenever we look at what does it do, it involves a temporal component. So we're looking at time-resolved dynamic processes. And I'm sure all of you are very well aware that we have tons of application of time series or of time-resolved processes. And that a lot of our current science and engineering applications want to analyze these time series and even forecast them. One of the hot topics, of course, currently would be climate and energy research, predicting weather, predicting energy consumption, predicting energy generation, all these sorts of things. But we also have temporal components in high energy or particle physics, in biology and medicine, which is what I did during my PhD. And if you take it even a step further, you don't only want to analyze and forecast temporal behavior, but you also want to use this in engineering application, for example, for condition monitoring, automated system control, process optimization, you name it. All of these things that we have, for example, in autonomous driving or in production, they all sort of rely on a temporal component. So this is sort of what we want to look at, and I've decided to start with an application that I've been doing with a PhD student together for the past 2 years, and that is very recent in terms of social impact or what concerns us, and that is energy research and specifically electric load forecasting. So predicting the consumption of electricity that we have on multiple levels. It might be in your own household by smart appliances and a smart meter. It might be on a regional scale, sort of for a city, for your local electricity provider, or it might be even on larger scales on the entire countries, where we want to predict how much energy or how much electricity will be consumed at what time of the day. Now, why is this important? Well, we all know that we are making the transition to renewable energy resources, and the production from these photovoltaic or wind generation is very volatile. However, the problem with our electric grid is that our generation must always equal our demand. If this is sort of tilted, if you pull more from the grid than you're producing, or you're producing too much, the power grid will become unstable and everything falls to pieces. So in order to actually generate power, we need to know how much we need. And this is not only sort of on a long-term scale or on a daily scale, but sometimes very, very short-time scales within a quarter of an hour, or even longer scales such as a week, because you need, in order to assure this grid stability, you always have to have a backup. You have to have resources. And if we have a look at Germany, if we can only be 0.1% more certain on the consumption of electricity, on our yearly consumption of 500 terawatt hours, if we take the current electricity price of 35 cents, this is roughly 175 million euros, or enough electricity to power 15,000 households. So just by having to keep these resources in case of volatility in the grid, we have a large costs, and the better we can predict consumption, the better we can plan, and the less we have to account for these things. Well, it hasn't taken long for people to figure out that AI, and especially deep learning methods, is sort of the state of the art that you want to go for if you want to predict time series. I'm sure most of you have heard about so-called recurrent neural networks and the LSTM, the long short-term memory. But what has really kicked things off is the transformer architecture, which came around about 5 or 6 years ago, originally developed for natural language processing. Well, time series are nothing else than sequences, just as well as a sentence might be. So transformers are very, very interesting if we want to, for example, predict electric load. If we go to applications, we can actually leverage certain characteristics of our time series, which is what we did with our project or our model, which is called Recycle, standing for residual cyclic transformers, where we built a very efficient transformer architecture that can leverage patterns in time series data. If you look at the image on the right-hand side, we see that electricity consumption follows a very distinct pattern. Naturally, it's the day and night cycle. And we can even see weekly cycles, sort of weekdays versus weekends. And knowing that we have these patterns, we can put this into our model and thus be more accurate in our forecast, because we can train our model to focus on modulations of these already known patterns. We can add metadata about weekdays or seasonality and these sort of things to improve the model. And this actually helped us to improve on predicting electricity consumption for Germany against current state-of-the-art transformer networks, just as the vanilla transformer or the so-called FET-former, which is one of the latest greatest in time series forecasting. But the fun thing is, once you've figured out one use case, electricity demand or electricity consumption, you can also transfer this to other domains. For example, water demand, which is a collaboration that we have with the Siemens together. Or you can start predicting temperature from certain measurements. And in all of these, you actually yield better results. But I mean, this is all nice and fun and very theoretical. If you say, okay, I can predict now with 0.5% better or even 0.2% better these things. But I mean, we're not talking sort of theoretical things or just something in the lab. Ultimately, we want to predict things that target the entire society. And if we want to apply machine learning methods and deep learning to such complex systems and even critical infrastructures, which our electricity grid or water supply really are, then we need to have robustness. So one of the main pillars that we want for machine learning and science and engineering is robustness. Now, the term robustness can be interpreted very, very broadly, as I'm sure you know. When I talk robustness, I mean uncertainty quantification. Why? Well, I'm a physicist, and we were taught that no measurement that you do or no prediction is worth anything unless you have an error bar, right? I need to know how likely it is that I'm wrong with my prediction just as much as the actual prediction value itself. If we look towards AI methods, there is basically one can distinguish between two types of uncertainty. The uncertainty that arises from the data itself, because it is noisy data, because we have measurement bias, these sort of things. That's called aleatoric uncertainty. But machine learning and deep learning in enough of itself are optimization procedures with non-smooth, non-optimally convex loss landscapes. So we have an uncertainty arising from the model itself, and that is called epistemic uncertainty. The model sort of has a systematic bias in itself. And there's different way to go about this and quantify these uncertainties. You can go via ensemble methods, which is sort of intuitive. You run the model multiple times with variations. For example, you use Monte Carlo dropout, and then sort of have an ensemble of predictions. But taking it even a step further, you can think of so-called Bayesian neural networks, where the free parameters of the model itself, so our neural network weights, are not deterministic scalar values, but they are probability functions. So I can quantify each weight not with a single value, but with two, assuming a Gaussian distribution. And that would help me in actually capturing how certain the model is, both with respect to data as well as its weight. And then I could do something that is shown on the right-hand side in the graph, which is I can make a prediction for the time series, but I can also draw such an error bar around it, trying to capture in which cases my model seems to be very certain. So I can plan a bit more strictly, or where it is very uncertain, so I have to be a bit more conservative with planning. And this is actually the project that we are looking into with my BMBF funded group, which is efficient methods for uncertainty quantification, specifically in transformer architectures. Now, why transformer architectures and why is it important there? I'm sure you all know that these transformer architectures do not come cheap. If you've seen some numbers around GPT-3, which has 175 billion parameters, or even ChatGPT, which is now built on advances of this, these models are huge. And this is sort of the crux with transformers, that they are very, very computationally intensive. And if I now want to do uncertainty quantification, I add even more compute load to this. If I run an ensemble, just as I do in simulations, I don't have to run the model once, I have to run it multiple times. And if I go even a step further to quantifying the model Bayesian in itself, then I double at least the amount of parameters. So my model just blows up immensely. So we need to find ways to speed up both training and inference and handle sort of the demand for compute, which is what the group is looking into. Now, transformers and the curse of dimensionality. This is something that we're experiencing currently because there are sort of two laws we figured out in the last 10 years about deep learning. That is, more data yields better performance. And if I'm in this context, I talk about predictive performance, not computational performance. So more data is better, and more parameters just make the model bigger. This is shown here on the plot exemplary over time, over the last 5 years. These transformer models, in that case for natural language processing, but we see similar trends in other application domains as well. They are just growing and growing and growing in number of parameters. And we're not talking a few million, we're talking billions, hundreds of billions. Yeah, that's a problem. And then with the attention mechanism comes another problem, and that is that it scales quadratically with the length of the sequence. So the sequence length is, for example, the length of a sentence, how many words I have in this. If I want to do time series, well, it's the number of time steps I'm looking at. If I want to make a prediction for 7 days at an hourly basis, that's 7 times 24. That squared is just the attention matrix. So I not only have a problem in number of parameters of the model itself, but also in between computational steps that go beyond the capabilities that we have currently in memory, in just storing these things. And that is why and that is why these models, they are not only trained on single GPUs anymore. We are talking really large scale AI by now. I have a list here of current state of the art transformer architectures, not for natural language processing, but for actual scientific applications. So AlphaFold 2, for example, which is, I think, by now very well known for protein folding, was trained on 128 GPUs, which is roughly one A100 GPU for 3 weeks. Or current weather forecasting models that take something between 64 A100s, 192 V100s for days. That's not little anymore. It's not something that you run on your conventional computer. And this is why the second pillar of our research builds on scalability. We want scalable AI models. And we are looking sort of at data and model parallelism. And what this is, I will explain to you in a second. Now, the first steps we did in this direction, and this is sort of where also my interest in distributed computing started, and also my collaboration with KIT was something that I did when I was still at DLR, which is the Helmholtz Analytics Toolkit, a framework for distributed and GPU accelerated tensor computations that is developed jointly by KIT, Forschungszentrum Jülich, and DLR. And the idea is that heat is basically distributed NumPy or distributed PyTorch. So what we did was we took PyTorch and we glued it together with MPI, so that you can do distributed tensor operations on GPUs. We have a lot of low-level NumPy, like array computations. You can do averaging, you can do matrix multiplication. There are some rudimentary linear solvers in there. And built upon this, we implemented a number of machine learning algorithms, specifically clustering and regression algorithms, very similar to sort of your scikit toolbox. The only thing is you can do this distributed, you can do this multi-node, multi-GPU with actual MPI as over the interconnect fabric. Now, a lot of people started saying like, well, but there is something like this, right? There's Dask. And I'm sure those of you who work with Python have heard about Dask. Yeah, we are faster than Dask. Why? Dask uses task scheduling, whereas we with Heat have actually truly parallel algorithms. And here is just like some actual scaling experiments, both weak and strong scaling, of comparing Heat on a CPU, on GPU, versus Dask and the original PyTorch implementations for a CDist function. So calculating pairwise distances, which is something that you need for quite a number of clustering algorithms. If you look at like k nearest neighbors, this is something very common. And the other one is actually a machine learning algorithm, which is k-means. And we are by orders of magnitude faster than Dask. Because it is actual MPI. I'm sure I don't have to tell in this round what the benefits of this is. Yeah, so this was sort of the start into scalable machine learning. But of course, the current hype is neural networks, right? And if we look at neural networks, we have two strategies for parallelizing them. There is data parallel, which just means you're splitting your data. So you have each process, whatever your process is, a GPU, a node, regardless, has a copy of the model and gets a shard of the data. And you do synchronization updates of the weights in between. There is a question. Okay. I will go later on onto this. And the other thing is model parallelism, which is much harder because you're actually distributing the model across nodes. And I'm sure you know how a deep neural network works. If I have parts on one GPU and other parts on another GPU, I need a lot of communication. What people generally look at is pipelining. So you put whole instances of the model, such as layers or multiple layers together on a process. But coming from a parallelization approach, that's not truly parallel, right? You're still sequential. You're alleviating your memory bottleneck, but you're not having actual parallel processing. And in general, model parallelism can be seen arbitrarily. It just means you're distributing your weights across multiple. So we are working in that regard as well. And this comes to the question that was just in the chat. And we've developed an algorithm for actual model parallel training of neural networks. Because as I said, each process holds a copy of the model and runs the typical forward-backward path. And in between these forward-backward passes, right, you have to synchronize the model so that every process still has the same model. Now, the typical approach, if you use your common PyTorch distributed data parallel framework, does this synchronously. So you wait for each model, for each process to perform a forward and backward pass, and then you synchronize. Synchronous is always prone to have a bottleneck. So another approach is to do this asynchronously. If you have a sort of parameter server or something, that can be very well done, but you run the problem of stale gradients. One model instance might be way faster than or way slower than the others. And by the time it yields its results, well, they are outdated because the weights were outdated. And the idea of one of our PhD students, Daniel Copeland, was to actually use a hierarchical structures or leverage the hierarchical structures that we have in HPC clusters with GPUs anyway, because you have multiple GPUs on a node, which are typically connected via very, very fast connections, such as NVLink. And then you have sort of a slower connection between nodes via the interconnect fabric. And you can sort of leverage this this structure and saying on a node, the updates between gradients are faster and more often, thereby counteracting these stale gradients. But over the interconnect fabric, I only go every couple of iterations or so to keep sort of the streamlined direction. And this is the so-called distributed asynchronous and selective optimization algorithm, or short DASO. And Horrorwood came up. Horrorwood is a framework developed by Uber for data parallel model training. And with DASO, you can train your models up to 34% faster at the same level of accuracy. In that case, validation top 1 score. And this actually scales up to 256 GPUs rather nicely. If you go beyond that, you get actually pretty nasty artifacts with distributed training anyways. So yeah, going there, we actually compare better than Horrorwood. Okay, and then a bit even further out, if we look at optimization from an even broader scope, something that you have to do in neural network training quite a lot is hyperparameter optimization. So tuning the setting of your model, or even neural architecture search, finding optimal architectures, number of layers, etc. for your model. And the typical way this is done, I mean, there is optimization or optimization theoretical approaches for this. The typical way is the PhD student approach, which is try and error. This sort of corresponds to what we call random search, as opposed to grid search, where you actually have a structured grid of hyperparameter combinations that you try out. But I don't need to tell you that given a very large space or dimensionality of your hyperparameters, this takes quite a long time. And especially if you have like neural networks that you want to train for your optimization, this is not very feasible. But you can actually use better optimization algorithms. And one type of algorithm along that line is evolutionary, which are bio-inspired optimization algorithms that sort of imitate natural selection, breeding, and then mutation in the genome. This is a work, I forgot to put the reference, unfortunately, but a work of one of our PhD students that was presented at ISC a couple of weeks ago on actual asynchronous communication for an evolutionary algorithm for such hyperparameter optimization. Why is asynchronous communication here absolutely key? Because if you do hyperparameter optimization or even neural architecture search, the evaluation of your models or evaluation times of your models vary greatly. Hyperparameters have a large effect on number of epochs you need for convergence. And if you do synchronous optimization and with synchronous updates, you will have a bottleneck by the slowest of your candidates evaluated. And by going asynchronous, we can actually speed up this process massively up to 3 orders of magnitude. And this has been actually employed to quite a number of projects that we use here in applications. And yeah. Okay, but I've been talking quite a bit about large scale and multi-GPU, and there is something that we need to talk about, which is a trend currently in AI, and that is using more compute, using more parameters, just buying better results. And that is unfortunately the environmental footprint that we leave with this. This is now estimates, again, for large language models, but having shown you the training times that we have for scientific applications, you can sort of extrapolate where we are heading with this, where we have different model architectures, GPT-3 being quite known currently, with a number of parameters, the hardware they were trained on, which is even beyond anything we've seen so far for those scientific applications, and also the estimated CO2 footprint of this. If you look at GPT-3, this is 500 tons of CO2. OPT, which is sort of an open source initiative with less parameters, claims that they are way better because they only use 70 tons. Yay. Because these numbers are sort of arbitrary, here's a comparison to sort of human scales. If you fly from New York to San Francisco, your per person environmental footprint is 900 kilograms of CO2. And the entire lifespan of a car, including fuel and everything, is 57 tons of CO2. So way below what we need to train these large language models. And keep in mind, those are single training runs. If you want to develop a model, you do this over and over again. I mean, there is the number with the neural architecture search for transformer model that is something at 280 tons of CO2. This is not feasible. We cannot go on like this, let alone that very, very few compute centers have actually the means, the infrastructure, the hardware to run these models. I don't need to take my bike to work to save fuel and then run large models the entire day on our cluster. This is sort of hypocrisy. So, but this is a trend that we see in deep learning because the hype is so strong, because the community is really only focusing on predictive performance. And we are buying better models by only a few percent or even per mil with larger models. And this trend, this research trend, is completely disregarding any economical, ecological, or social costs. We know that there's actually a logarithmic relationship between the performance and capacity. So there needs to be a cap towards this. And this is why we focus on actually efficiency of our models. And again, what I mean by efficiency is energy efficiency. So how can we train models with less energy? Well, the first thing that you need to do is to assess how much energy you're actually using, because those numbers are estimates that came in sort of meta studies afterwards. Most of the AI research are not aware of how much electricity they are consuming. In that regard, we are actually doing some community outreach. The last one happened a few weeks ago, which is our AI Hero Hackathon on energy efficient AI. It's something that we do together with different Helmholtz platforms, so Helmholtz AI, Helmholtz Imaging, and the Helmholtz Metadata collaboration. In the second instance, we actually did this in collaboration with NHR KIT. And sort of the two centers are KIT and DKFZ, which are driving this. And the idea is that it's a hackathon. You know, you get a task, you build a model on two real-world use cases for energy and health. These vary. And the idea is build a model, but make it as energy efficient as possible. And through that, we measure electricity consumption of all the jobs that the participants submit during their 3 days of hacking. So they sort of get a bill on their electricity consumption afterwards. And then we measure the inference energy. So how much does it cost me in terms of watt hours to make a predictions? And then the winner is announced by trading off prediction accuracy versus electricity consumption. And the whole idea of this is just to raise awareness and to make especially young research aware that it's not like, okay, I can run one more optimization, I can run one more model trial. What does it cost? It costs us a lot. Building up on this, on the first round of the hackathon that happened 1.5 years ago, we actually conducted a further study with the use cases that we used in this hackathon. One was actually electric load forecasting for 7 days, and the other one was X-ray image classification for COVID. And we used these use cases to actually profile energy consumption of AI workloads. So how much energy do I need during development, during inference, and how does this relate to predictive performance? Now, what is typically done is you just take your runtime of the model and you multiply it by your maximum power draw of your GPU, which might be, I don't know, 400 watts. And there you have your electricity consumption. But what we figured out during these experiments was an AI workload is not only GPU computation at maximum utilization. For example, if you run a recurrent neural network or an LSTM, you're not 100% using 100% of your GPU. You're using maybe 10%. So one of the biggest problems is inefficient hardware utilization where you don't actually need it. The next thing is we have data loading, data pre-processing, shifting data from CPU to GPU and back. And that actually contributes to the energy consumption as well. That's why we run our experiments at HiCore, which is a part of Horeca. And Horeca has Lenovo's X-Clarity controller as power sensors on the nodes installed. So we get actually very precise measurements of the whole node electricity consumption. And at the same time, we used the vendor library, specifically the NVIDIA SMI, to track GPU energy consumption and have a look at this. We used different configurations of nodes, your standard GPU node with just a single GPU running, but also CPU only nodes, just to see maybe for certain cases, the CPU does not fall that far behind the GPU. And in fact, for the energy use case, which was a univariate time series forecasting problem for prediction, even though the runtime was much larger than on GPU, you can see this with the runtime of 9 minutes versus 5 minutes. The overall electricity consumption of the job on the CPU node was comparable to that of the GPU. So if you look at images for the health use case, there's no way in beating the GPU. But sometimes for a specific application, it might actually make sense to say, okay, even the idle consumption of the GPU is so high and I'm not fully utilizing it, it might make sense to you to move to CPU. And one fun fact for those people tending to use Jupyter, which we have as sort of interface to our cluster as well, the overhead for energy consumption is negligible. You get sort of the same as if you were to allocate an interactive job. But not everyone is as fortunate as we are to being able to actually measure whole world electricity consumption. And that is why another PhD student of ours set out to sort of help people in raising awareness and developed a tool that is called Perun. The idea is to use energy consumption for continuous benchmarking just as well as we do other things. So continuous electricity consumption benchmarking. And the idea is to have a very, very low overhead or lightweight Python tool that you can either use via the command line or as function decorators in your code. And this tool queries sensors if they are available, queries the respective vendor libraries, NVIDIA SMI, Intel RAPL, whatever you have. And for other components, such as data transfer, it at least gives you an estimate hardware dependent on your electricity consumption. And you can use this to get a bit more of an accurate estimate than just saying I ran 1 hour on a GPU at 400 watts. The tool is installable as a Python package. I know that Amitanshu, for example, from Harald Kasper's group at Erlangen is looking at this. But if you want to check it out, it's been accepted for publication at Europa. But just look at it, GitHub Perun. It's really, really cool in order to measure energy consumption. And going forward, we want to actually use this to do dynamic voltage and energy scaling of different hardware components on the node, sort of limiting these components during code execution when we see that they are unutilized. This is sort of ongoing work. Okay. And then something that was talked about this morning as well, but that is, let's have a look at actual energy consumption of larger models in more detail. And for that, we chose a use case from climate research, specifically from weather forecasting. Why? Because I find it rather hilarious that our current weather prediction or climate models consume a lot of energy in order to predict, the changes in climate change. Okay, this is not true. Why we chose it? The reason we chose this model was there's actually a state-of-the-art transformer model that is large scale, that works distributed, both data parallel and model parallel, and runs for a longer period of time on multiple accelerators, such as like 1 day on 64 GPUs. So we actually have a model that is large enough, that has large enough a power draw to study certain effects. And that is ForecastNet, which was developed last year by NVIDIA for weather forecasting on a scale of 7 days. It combines the vision transformer architecture with so-called adaptive neural operators, a sort of operator learning. And as I said, it leverages both model parallelism on a node by splitting up the model across 4 GPUs or 2 GPUs, whichever you like, connected via NVLink, and then across different nodes, you use data parallelism to train the model. And the idea of this project, which is an NHR future project, is to measure the energy consumption and try to relate it to both to computational performance. So actually looking at how well is the model performing computational wise, as well as scaling. Sort of do scaling experiments, but instead of looking at throughput, look at energy consumption. And maybe we might find a sweet spot on distributing our model on a certain number of nodes and GPUs. Yeah, this is ongoing research. So with this, I am coming to the end of my presentation. The 3 pillars that we are investigating are robustness, scalability, and efficiency. Currently, we are looking into uncertainty quantification, a lot of work on model and data parallelism and energy consumption. But there is more to come, more to investigate. We have tons of ideas looking at uncertainty quantification, looking at not only time series forecasting, but actually anomaly detection, going beyond classical training by using bio-inspired optimization or bio-inspired neural network training for maybe feed-forward only training, as is done in the neuromorphics community. A bit on this tool development or Python packages towards AI engineering for large-scale and distributed neural networks, and more getting into the domain of classical HPC, because of a lot of the things that we are lacking in today's AI research has been done for the last 20, 30 years in classical HPC and distributed computing. And I think there's a lot of potential to leverage the knowledge, to leverage things like accelerated numerical linear algebra, sparsity, performance engineering, and to bring these to AI, sort of to go beyond what the current community is doing. With this, I'm done. I thank you very much for your attention, and I'm happy to answer any questions.
Thanks a lot, Charlotte, for this very inspiring talk. Are there any questions or comments? Please raise your hand, unmute yourself, type it in the chat, whatever. Frank Alvaro is the first. Please go ahead.
Hi, thank you for the presentation. It was very interesting. I have a question in the context of NHR. Here in the NHR, we are trying to offer some sort of alternative access to the HPC system. That is seen to bring more scientists that might not be familiar with, let's say, classical Linux utilizations of HPC.
Yeah.
And you mentioned that your Python custom framework is some sort of parallel Python in the background that allows you to exploit the access to distributed GPUs, basically.
Yeah,
and
you're
you also
about
mentioned,
heat, right? Yeah,
exactly, heat.
Yeah.
And in that context, you also mentioned Jupyter, which is basically what we're trying to push our users towards when it comes to machine learning. And they themselves also requested as one of the frameworks to use. How usable is it for non-research purposes, the heat platform?
So far, I think we haven't figured out for us yet how Jupyter on multi-GPU works. In terms of usability, if you, let's say, if you figured this out in the back end, which has nothing to do right with a package, but if you can actually teach your Jupyter to use multiple GPUs and to sort of have an as run equivalent for your MPI code, then very, very simple, because the way heat is designed is it works just as PyTorch. So when you instantiate a tensor, you can just say how you want to distribute it across x is 0 or x is 1. It's just another parameter. And all the computations below, if you add, if you accumulate, if you do matrix multiplication, is done on the back end. So for the outside user, it works very much like NumPy. The problem I see with Jupyter would be more the connection to, because what you need is MPI. And if I'm not sure that we have figured this out. We use Jupyter for our cluster as well. However, you get like a single GPU with this or mix. But I'm not aware that the multi-process problem has been resolved yet.
The results you showed are done using batch jobs then? Yes.
This is the simple batch script submission via Slurm, specifying just the number of nodes you want to use and the number of processes you actually want to use to spawn on them, and then yeah.
Thank you for the clarification. That is a bit sad for us, but thank you.
If you have a solution, hook us up, because I think even if you think about data parallel training, right? If you were able to run on a single node a 4 GPU job, distributed neural network training with 4 GPUs in Jupyter, that would be immense.
We have efforts to do that, but I thought that if for some reason your heat framework already had a solution for it, we might not have to put extra effort on it. And if we were to put extra effort, we might do it for more popular frameworks, Pure, Keras, TensorFlow, and PyTorch, instead of a dedicated research one first.
Yeah.
And then we might move into that. But thank you for the clarification.
Yeah, sure.
Okay, more questions. I have a question, actually. It starts simple. The power generation problem, forecasting problem. So for me, who is used to things like Fourier analysis, okay, for me, this is a simple problem of Fourier analysis. Just take a long enough sample of the power dissipation or power that's needed and look at the Fourier components. And then as long as you take enough components, you can resolve as much detail as you like. Of course, you cannot capture exceptional events. Like if there's a thunderstorm over half of Germany, that will have an impact on the power consumption, but neither can an AI model do that. So what's the difference? What's the
I think the difference lies within the forecasting. So the idea is I put in the consumption of the last 7 days, and I can predict the consumption in the next 7 days. And I think if you do this via Fourier decomposition, you ultimately need to fit a model, right, to this. What kind of a model is, regardless. I mean, the statistical approach is going something with these autoregressive models, ARIMA and something. They are just not good enough anymore, especially if you want to do longer range forecasting. Predicting the next time step, that's easy. That you can do with an autoregressive approach, right? Rather simple. But if you want to predict multiple time steps into the future, it gets tricky. And actually, fun fact, a lot of the transformer architectures that are currently being used for time series forecasting are working in the Fourier domain. It's a bit related to what they're doing in ForecastNet as well. They transform their data into Fourier space and then perform the dot product attention there. And the power in the attention mechanism lies within being able to put different elements in a sequence that lie far away from one another into relation, but keeping sort of the temporal time. Because if I do this in Fourier space, I lose consecutivity, right? I just get frequencies. But the model, the attention mechanism knows the order of things, but at the same time, how two things within this are connected, which makes it predictive. It yields better predictions currently. But yeah, Fourier, going to Fourier space, if you have frequencies, is a natural jump to do this.
Speaking of the attention matrix, you said that the attention matrix is basically n squared, where n is the length of your sequence, and it's an n squared problem, but the attention matrix also is usually sparse. So not every word, every other word. So can we elaborate on the quality of being sparse?
Yes, we want, I mean, it really depends, because the way attention currently works is just scalar product plus softmax, right? For some applications, this might not work because the softmax also yields this sparsity. Sometimes maybe you don't want the sparsity. However, we are very certain that we want sparsity. It's a technical thing. Sparsity in neural networks is currently heavily researched. On the one hand side, just having sparse weight matrices, because it turns out 90% of the weights that we are training with, we don't need. For the attention mechanism, the same goes, right? We can throw this out. The problem is, how do you code this? Because so far our deep learning networks are all dense linear algebra, and moving to sparsity brings about quite a number of problems, both sort of technical ones and having something that can do sparse matrix multiplication, but also some of the effects of sparsity in neural networks are not fully understood yet. So we know they tend to be sparse, but we don't know in the beginning where they will be sparse. And still, if you want to leverage this sparsity, you can only do it after you've computed the attention matrix, right? Then you can cut and condense this. But in most cases, you're still like starting out with a dense representation and then pruning out things, which only saves you in the long run. If you do this for inference, then yes, but in training, it's quite tricky.
As a question in the chat, Dorothea, what is, in your opinion, the relative benefit of reducing training times versus making inference more efficient in terms of energy efficiency?
It really depends on the application. It really depends on what you want to achieve with your model. If you're looking towards edge computing or really like real-time deployment in condition monitoring, all these kinds of things, then inference is key. That's where you run your model. It's not a big problem if you have to train this once and then just, but then you can also press it on an ASIC or an FPGA, and then you have low energy consumption. There, it's more reducing model size. It becomes problematic if you have to train over and over again, or if your development energy at some point becomes large. And this is sort of a trend that we're seeing. You run your model again and again. One simple training run might not be that bad, but counting that you have to do this hundreds of times, there it becomes problematic. And then it's also a question of data size, right? Like how much data is going in there, because that also determines how much compute you have. So I'd say it really depends on what you ultimately want to do with your application. But in terms of research, what we're also looking like for proof of concept, find a new architecture that can predict this better. There we're not talking about deployment. There we're talking about training, finding new training algorithms. And there, I think it's very, very valuable to look at actual training. Because it's an argument that a lot of people bring, right? Ultimately, once I've trained it, then I can prune it. I can reduce precision. I mean, AI people have no problem in going to FP16 or even FP8. I mean, it's all rather approximate what we're doing anyways. But the amount of training and compute that we use to get there is often neglected. And for research, I think we need to start looking at this.